Okay, so in these notes, we're going to try to establish some rules for the means and variances of random variables. We're going to start with two different distributions. Here's our random variable x, and then here's our random variable y. Two different distributions. Let's start by finding the mean of x. So 2 times its probability, 3 times its probability. Add those up, we get 2.75 for the mean of our random variable x. Okay, and then this is actually the variance of x, right? If it's sigma squared, that's the variance. So it's everything involved with finding the standard deviation, except we just don't take the square root of it at the end. So let's start with 2 minus the mean, square it, times its probability, and the same thing for 3. Subtract the mean, so on and so forth. And our variance would be 0.1875. So just as a reminder, variance is still a measure of spread. We don't square root this one, right? If we square root it, it turns into standard deviation. Okay, and now let's talk about the y distribution. So y is our other random variable. What would the mean of y be? So let's take 4 times its weight, right? Each one of these categories has a weight, and then we add them all up. We had 5.2 for the mean of y. And then for the variance of y, sigma squared, take each value, subtract the mean, square it, multiply by the probability. So we have 0.760 for the variance of y. I hope you thoroughly enjoy my color coding. That took me a while, okay? And then before we get on, just one quick note to remind you. Sigma represents the standard deviation. Sigma squared, which is the standard deviation squared, is the variance, okay? So let's keep those things straight before we go any further. So we've already established the mean for x, the variance for x, and the mean for y and the variance for y. We're going to look at a few different effects. For the start, what if we do 3x? So 3 times our random variable x. You'll notice we just multiply these x values by 3. So now we have 6 and 9. And then the probabilities are still distributed the same. So the mean of 3x, we can calculate this again, and as you might guess, it's just 3 times the old mean. So 8.25 is really just 3 times the mean we got for x before. I think it was 2.75, right? So really we just multiplied it by 3 in this case. How about the variance of 3x? So what's sigma squared for this 3x random variable? And if you think the answer is just going to be 3 times the old variance, you're warm, but that's not exactly correct. So we could calculate this, 6 minus the mean, square it, probability, plus, and do the same thing for 9, right? Minus the mean, square it. We actually get 1.6875. So that's more than just 3 times our old variance. The variance that we got for x before was 0.1875. So this new variance is actually bigger than 3 times the old variance. So what is the number that we multiplied by to get this new variance for our 3x random variable? Well, if you divide this by the old variance, turns out it's 9. So the pattern would be, don't multiply the variance by 3. Actually, we want to multiply it by 3 squared. That's how we get 9. So we take the old variance and we multiply it by 3 squared to get the new variance here. Okay, but more on that later. Let's talk about the mean and variance for 5 times y. So take the y values, multiply each one by 5. The probabilities are distributed the same. The mean would just be 5 times our old mean, right? The mean of y that we calculated before, which was 5.20. So multiply that by 5, and we're at 26 for the mean of this distribution. And as for the variance, we don't want to just multiply 5 times the variance of y. We want to do 5 squared. So if we do 5 squared times the old variance for y, it's 25 times 0.760, 0.760, which is 19.0. 19.0. 19.0 Okay, so hopefully you're starting to get a little bit more comfortable with these rules. How about the mean and variance for 2 plus 7x? So multiply all the x values by 7, and then add 2. So the new mean, I mean, we could calculate this by hand, but now that we're starting to catch on to the pattern, the new mean would just take the old mean, multiply it by 7, and then add 2 to that answer. So if our old mean was 5.2, multiply by 7, add 2, we're at 21.25 for the mean of this distribution. And as far as the variance goes, I just want you to keep in mind that adding 2 won't change the measures of spread. So in this case, that plus 2 part won't change the variance at all. The only thing that will change the variance is the fact that it's being multiplied by 7. So this by constant 7. Let's handle that constant the same way we handled the 5 for the variance here and the 3 for the variance in this case. So we're going to multiply the old variance of x times 7 squared, right? Not just 7. The variance gets multiplied by 7 squared. So we have 49 times 0.1875, right? Our original variance that we got for x, which is 9.1875 for our new variance. Okay, so these are just a few examples to illustrate some linear transformations of random variables. So let's generalize this to a formula. So if we start with the random variable x, and then we multiply it by some constant, say b, and then we add a constant to it, say a, the new mean would just be b times the old mean plus a. So that's actually nothing new. We did that in the previous notes. What's new, let's think about the variance for a second. So what we just showed with these examples is adding something like a, adding a constant won't change the variance. However, multiplying by a constant, like b, means that our new variance will be the variance of x times b squared. Just like we multiplied by 7 squared here, or multiplied by 5 squared here, or in this case it would have been 3 squared. So that's the rule for the mean, that's the rule for the variance. And then as far as the standard deviation goes, we actually did the standard deviation in the last notes. Keep in mind the standard deviation, and let's use the same notation here. This would be a plus bx as our random variable. The standard deviation is just the square root of the variance. So if our variance is b squared sigma squared x, when we take the square root of that, it's just b times sigma x. And that's the rule that we established in the previous notes. One thing to keep in mind, though, standard deviation can never be negative, even if you're multiplying by a negative constant here. So we say the absolute value of b, the multiplier there. Okay, and then the last part here just says, it doesn't even show us a distribution, but it says based on these rules, give the mean and variance of 3 plus 2y. So we could actually make that distribution table ourselves, but there's really no need to. Let's start with the mean. So the mean's really straightforward. We would take the old mean for y, multiply it by 2, and add 3. So if the old mean for y was 5.2, then the mean for this distribution, the 3 plus 2y distribution, would just be 13.4. Okay, and then for the variance, remember adding a constant like 3 doesn't change those measures of spread. So the only thing that's going to affect the variance here is this 2 multiplier. So we're going to take the variance for y and multiply it by 2 squared. So sigma squared y times 2 squared, which is 4 times 0.76, or 3.04 for our new variance. Okay, so let's go on to the next page. So we've already established x and y. We've already got the mean for x. We did these early on in the notes. The next part here says if x and y, and the key word is independent. If x and y are independent and added, then the sum x plus y takes the following values listed in the table below. Find the probabilities. So you can imagine there's a few different ways to add together 2 and 3 to 4, 5, and 6, and you could come up with these numbers, 6, 7, 8, 9. Our objective is to fill in the probabilities that go with each one. For example, how rare is it that you get a 9, or how common would it be to get a 7 if we use these distributions for these values? Okay, so here's what I'm going to recommend. If you're a visual learner, let's draw a probability tree. So let's start with our first branch, our first layer here. This is going to represent the x distribution. So in the x distribution, you can either get a 2 or you can get a 3. And then let's put the probabilities on our branches here. So a 2 would be a 0.25 probability, and then a 3 is a 0.75. And then regardless of whatever your x value is, you're going to get a y value of either 4, 5, or 6. They're totally independent, so we're going to branch off another layer from each one of these branches. So it doesn't matter whether you got a 2 or a 3, you still might get a 4, a 5, or a 6, a 4, a 5, or a 6 from the y distribution. And let's fill in the probabilities on those branches. So a 4 is 0.3, a 5 is 0.2, a 6 is 0.5. There we go. So now we can actually map out a few roots on this tree to see, for example, what's the probability I get a 6, right? Maybe these are two die, right? You roll the x die first, you either get a 2 or a 3, and then you roll the y die, you get a 4, 5, or a 6. What's the probability you get a sum, one number from x, one number from y, and you get a 6? Well, 6 would actually be the lowest possible sum you could get if you add a number from x and a number from y. And there's only one way to do it. You get a 2 from the x and a 4 from the y. So since these are independent probabilities, we can just multiply right down the branches. So that's 0.25 times 0.3, which is 0.075. And that's the only way we can get a 6, so I'm going to put 0.075 down here in the probability distribution. All right. How about, can we get a 7? Well, we could either go 2 and 5, or we could go 3 and 4. So there's two different roots. We'll add up those two different roots. So for a 7, we could go 0.25 times 0.2 down this branch. Or let's add in that other root. We could go 0.75 times 0.3 down this branch if we went 3, 4. So if we add up those two possibilities, we have 0.275 for our 7 category down here. Okay, then how about an 8? Well, we could go 2 and a 6. That'd get us to an 8. Or we could go 3 and a 5. So to get an 8, 2 and a 6 would be 0.25 times 0.5 for that root. Plus, if we go this route, it's 0.75 times 0.2 for a grand total of 0.275. And lastly, for the 9, we'll illustrate it here, but you could just subtract all these from 1 and get what's left over, and that would be your answer for 9. There's only one way to get a 9. If you go 3 from the x and 6 from the y, so that'd be 0.75 times 0.5, which is 0.375. Okay, so now that we've combined x and y, we have this new random variable. It's called x plus y. So what would be the mean of our new random variable? So what's the mean of x plus y? And we could totally do this by hand, right? 6 times 0.75, 7 times its weight, plus 8 times its weight. And when we get there, you'll notice it's actually just the mean of x plus the mean of y, which we already have those two numbers. So the mean of this distribution would just be 7.95. It's the sum of those two means. And then for the variance, we could calculate this by hand as well. And you may or may not guess this one. The variance is actually this variance of the x variable plus the variance of the y variable. We know both of those. Variance for x plus the variance for y, which is 0.947. Which Little side note here, to get the standard deviation for x plus y, we'd have to square root that value for the variance. So the square root of 0.947 would be approximately 0.97314. That would be for the standard deviation if we felt like taking the square root of the variance here. So in general, if x and y are independent random variables, what's the mean of x plus y look like? So if we have a combined distribution here, a new random variable, the mean is actually pretty straightforward. It's just the mean of x plus the mean of y. Coincidentally, the variance is actually really straightforward too. It's the variance of x plus the variance of y. Just keep in mind that only works when x and y are truly independent random variables. If they're dependent, it's not so obvious. This formula actually gets more difficult, but by and large, we're only going to deal with the independent case. So this actually works really nicely. The next part says, does the same hold true for subtraction? So if we did x minus y, here's the values we might come up with, and then there's their probabilities. So if we were to show the mean by hand, our value is equivalent to taking the mean of x and subtracting the mean of y, which we know both of those, which is negative 2.45 for the new mean. Okay, so that really shouldn't be surprising. What may be surprising to you is that the variance of this x minus y random variable is actually the exact same as the variance we got when we took the sum. So the variance is still 0.947. So why is that? Well, two reasons. One, the variance can never be negative, right? We square everything when we calculate the variance. Two, variance is a measure of spread. It's a way to measure variability. And when you combine two random variables, even if you're subtracting them, you actually add variability, right? Things get more variable. So that's one way to remember that. Even when you're subtracting items, the variance will always add. Because in a way, you're still combining two random variables, and that creates more variability. So we have to account for that. So really important note to make, don't forget that. Even when you're subtracting two random variables, your new variance will always be the sum of the original variances. Okay, so the last part of these notes looks at a few different cases. Most importantly, it says in statistics, up here in italics, in statistics, 3x does not equal x plus x plus x. And I know that's what you're used to from algebra, but it's not true in statistics. And the reason being is because those x's in statistics represent random variables that may be independent from one another. So it says, consider a game of chance in which the player draws numbers from a hat. The numbers in the hat are numbered 1, 2, and 4 with the following proportions. So there's the chances that you get a 1, there's the chances that you get a 2, and there's the chances that you get a 4. So by now we've had plenty of experience calculating the mean for a discrete random variable like this. So the mean in this case would be 1.7. The variance, let's calculate the variance first. The variance is actually what we'd calculate first, and then the standard deviation. So the variance in this case would be 0.81, and then to take the square root of that, we'll get our standard deviation of 0.9. Okay, so the first case says draw one number from the hat and triple the value. So whatever number you draw, you're going to triple the value. So our new random variable y just takes x and multiplies it by 3. So 1 became 3, 2 became 6, and then 4 became 12. And then the probabilities are still distributed the same. So the new mean would just be 3 times the old mean. So 3 times 1.7 is 5.1. The new variance, well, we would just take the old variance and multiply it by, well, not 3, but 3 squared. So 3 squared times our old variance of 0.81, which gives us 7.29 for our new variance. And then for the standard deviation, we would just take the square root of this number, or, as far as the formula is concerned, the square root of 0.81 is 9, and the square root of 3 squared is 3. So 3 times the old standard deviation gives us 2.7. Okay, so case 2 is actually different. Case 2 says draw 3 numbers with replacement, so these are independent draws, and add the values. So this new random variable z is x1, the first draw, plus x2, the second draw, plus x3, the third draw. So those are 3 independent events, and we have 3 independent random variables to make our sum now. So if we do that, first of all, we have a lot more choices as far as the outcome is concerned. So this illustrates why 3 different random variables together is different than just 3 times a single random variable. So let's start with the mean of z. And z is our combined random variable, right? Our new random variable. So z is the sum of 3 random variables, x1, x2, and x3. So for the mean, we would just say, what's the mean of x1 plus what's the mean of x2 plus what's the mean of x3, which we know the mean of x actually. It's 1.7 for each one of those guys. So 1.7 plus 1.7 plus 1.7 gives us 5.1 for our mean. Okay. So no major surprises there. Let's go to the variance though, sigma squared z down here. So to get sigma squared z, we're going to take the variance of x1 plus the variance of x2 plus the variance of x3. So we're going to combine 0.81, that's the variance for x, right? 0.81 plus 0.81 plus 0.81, which is 2.43 for our new variance. And we can use this variance idea to help us get sigma. So sigma sub z here, we would take the square root of the variance. In other words, we start with the variance of x1 plus the variance of x2 plus the variance of x3, which we've got right there, and then we square root that whole thing. So each one has a variance, we add them all up, and then we square root that answer, which gives us 1.559. Or, in this case, we just took the square root of 2.43 to get 1.559. Okay, so looking at all those different cases and all these examples, can we come up with some general rules? So if we have the mean of not just x, but n times x, so we multiply a number times x, our random variable, our new mean will just be n times whatever the mean of x is. Our new standard deviation, which we did this in the last notes also, would be the absolute value of n times whatever the standard deviation of x was. And then our new variance, which we did a bunch of in these notes, would be not n times the variance, but n squared times the variance of x. Okay, and I hope you see the difference now. With this case, this is n different random variables. Right, so this is n different x's. Basically, you can think of playing the game, like in this example above, playing the game n times. Well, turns out the mean, you would just add up the mean n times for each one of those x's, so the mean is still n times whatever the mean of x is. And then for our new variance, sigma squared, we just add up n variances, right? In this case, we added up the variance 3 times. So n variances would be n times sigma squared. And we just illustrated that with this example, like 3 variances in a row, so it was 3 times the variance of x that gave us 2.43. And then for our standard deviation, the last part on here, we would just take the square root of n times the variance. So if we take the square root of that, we'd have the square root of n times just sigma, because the square root would cancel with the square. So we'd be left with square root of n times the standard deviation of x. Okay, on top here, this is the case when you take a random variable x and multiply it by a constant. And then on bottom, that's when you have the sum of multiple random variables. Like in the example, we had x1 plus x2 plus x3. So 2 totally different cases. On the top, that would be the example like when we did 3 times x. This one is 3 different independent random variables being added up. Okay, so hopefully these examples helped illustrate to you the rules for means and variances of random variables when we're combining them or multiplying them or otherwise transforming them. That's all for these notes. I'll see you in class.